Okay. Hello, everyone. Welcome to Module 8. So the topic for Module 8 is magnetic fields from currents. So we're going to talk all about how to calculate the magnetic field that is generated from a current carrying wire. So we now know from the last module that when you have moving charge through a wire or otherwise, that moving charge creates its own magnetic field. And then we also know from the last module that when you have moving charge, it is and you expose that moving charge to an external magnetic field, there is a magnetic force acting on it. And so we're going to sort of like delve into that a little bit further and look at two specific laws that allow us to calculate the magnetic field if we know what the current is. Okay, so I'm going to make two videos this week. The first video is just going over this Biot-Savart law, which is one of the laws. It's the sort of fundamental law that allows us to get magnetic field from current. And then the second one is called Ampere's law. And it does the same thing in a much easier way. It's a little bit like Gauss's law. It's sort of a shortcut that allows us to avoid the complicated integration that is part of the Biot-Savart law. Anyway, so both of these topics or both of these laws are ways of figuring out the B field from a current carrying wire. Okay. So we're going to start with this one. So what this one allows us to do is it allows us to take an arbitrary distribution of current. So like there doesn't have to be symmetry in order to use the Biot-Savart law. So you can have any arbitrary distribution of current. And from that, you can calculate the B field. Now it's the case where like you always want to try to avoid using this if you can, because you'll see in a second that it involves an integral, and that's where Ampere's law comes in. If you have like a symmetrical, like a straight infinitely long wire, or a solenoid or a toroid, then you can manipulate the symmetry of that charge carrying wire to find the magnetic field in a lot simpler way without having to integrate. Anyway, it's important to note that the Biot-Savart law is considered to be the fundamental link between electricity and magnetism. It basically explains how current generates magnetism, like how you can get magnetism from charge, which is like an amazing thing. Okay, so like I'll just note that down. It's the fundamental link between electricity and magnetism. And the reason for that is it allows us to go from like from electric charge, which we talked about at length for the first part of this course, to magnetic field. Okay. And like the electric charge is in the context, this is moving electric charge, obviously. And it's in the context of like current in a wire. Okay. So that's the Biot-Savart law. The so Ampere's law is another way, a simpler way of finding the B field. Okay. But to use it, you need symmetry in the wire. So like you can't have a wire that is like all sort of like bent and crossing over itself, and it has to basically be a straight wire. Or a solenoid, which we'll talk about in the second video, or something called a toroid, which we'll also talk about. So like the way I think of this is like Ampere's law is to magnetism as Gauss's law is to electrostatics. So it's like Gauss's law for magnetism. Okay, I kind of equate the two things in my mind. Okay, so let's get so the rest of this video is just going to be looking at the Biot-Savart law, and then the second video that I'll make will be Ampere's law. Okay, so what the Biot-Savart law allows us to do, it allows us to calculate the magnitude of the B field. Okay, but not the direction. The direction you already know how to find. The direction comes from the right-hand rule, okay, which we've already covered last week. Okay, so let's look at it. So this is the formula for the Biot-Savart law. This is just a constant. Okay, so we can almost ignore it. Okay, I is current, like how much current you have running through the wire. DL is an infinitesimally small, it's an infinitesimal length of wire, segment of wire that we use to set up our integration. Okay, R is the distance from the wire to the point that we're interested in calculating the B field, to the point we want the B field calculated. Okay, and then this is just like DL cross R hat. So it's like it's the cross product between that infinitesimal length of wire and the vector that connects the wire to the point that we're interested in. So R hat is just like a unit vector in that direction. Okay, so we you almost never use this law. It's good to see it like once in terms of like how it works, and then basically you just know what the formulas are that come out of this integration for the different types of symmetries. Okay, so like I'll show you like an example of how you could derive like one of the results that comes out of this, but like almost never will you start with this. It's just good to see it once. Okay, so like if you have, so I'm just gonna write like all of the different results. Okay, so if you have a long straight wire, the result of this integral is just the B field equals mu naught times the current over 2 pi r, where r is the distance from the wire. Okay, if you want to see like how you go from this integral to this, it's in the first part of the collage like material. Okay, so you can if you're interested in like how the integration works. Okay, so that's one. That's one geometry that is good to know. What color should I use? Okay, so let me just erase this. This is in the way. This is a constant. Okay. So the result of this integral, if you have a loop, is just B equals mu naught I over 2r, where r is the radius of the loop. Okay, so that's another result. I'll derive this one for you in a second. Okay, I think it's nice to see one example. So I'll do this, I'll kind of like do it out, like how you go from the integral to that in a sec. Okay. So if you have a solenoid, then the result of that integral is just mu naught times n times the current. Okay, and I should say this is a long solenoid, just like this is a long wire. Okay, similar to when we were talking about these symmetries in the context of electricity, in order for you to have the components of the B field like cancel out, you have to and so such that it doesn't matter with in the case of the solenoid, it doesn't really matter where you are relative to, you need to consider like a really, really long one. Okay, so you're almost assuming that it's like infinitely long. Okay. So and n in this case is the number of turns of the solenoid. We'll talk more about this in the second video. The number of turns in the solenoid. And I is just the current. Okay. And then the last kind of like result of this integral is something called a toroid. So a toroid is an interesting shape. It's basically a solenoid. So a solenoid is just a coil. Okay, it's just like a wire that goes like this, and it's connected to it's got current running through it. Okay, and the B field is concentrated in the middle of it. So I mean, depending on which way the current is going, the B field is like is concentrated just in the center of the solenoid. Okay, and so like if the current is going, like up, then the B field is in this direction according to the right-hand rule. If the current is down, then the B field is that way. But so it depends on like the overall, direction. It depends on the direction of the current as to whether this arrow is pointing up or down. But that's what a solenoid is. A toroid is if you took that solenoid and you made it into a donut. So it's sort of like it's like imagine I take the solenoid and I like wrap it up and I close the loop. Okay, and so the B field, this is hard to draw. The B field is through the center. It's trapped inside the solenoid. That's the B field. Or sorry, not the solenoid, the toroid. Okay. We'll talk about this more in the second video, but just so you have it and sort of like see all the possibilities of the geometries, the B field of a toroid, if you were to do this integral, which I would never want to do, for a toroid, you would get this. Okay, again, where this is the number of loops. Oh, sorry. That's the wrong one. That's the solenoid one. Excuse me. It's just Ni, number of loops, but it's divided by 2 pi r, where r is like the distance from the center of the toroid to where you are inside the coil. Okay, so this is basically, so that's R, what I marked on the chart right there. Okay, so those are all the geometries that you could ever really want to know. Like any problem that you encounter will have one of these 4 geometries. And in the second video, I will explain to you how you get I'll derive each of these 4 equations from Ampere's law. Okay, so you can get these 4 equations from this integral, the Biot-Savart law, or from Ampere's law. It's like the outcome is the same. It's a lot easier to get them from Ampere's law. But if you're interested in knowing like how the integral is set up and what it looks like, this one is in collage, and this one I will do in a second. Okay, and then the solenoid and toroid, you can look those ones up if you're interested. Okay, so let's talk about the magnetic field at the center of a current carrying loop. So this is where I'm going to basically derive this. Okay, so there's two ways. There's two ways that you could do this. The first way is with the Biot-Savart law. And the integration. And then the second way is just basically manipulating the symmetry of the arc. Okay, so let's say that we want to know what is the magnetic field at the center of half of a loop. Okay, so let's draw that. So let's say that you've got half a loop. Okay, and like the other half is not there. And I want to know, and this has got like a radius r. And I want to know what is the B field, like right there. B field there. Okay. So we're gonna do the painful way first and then the nice way second. Okay, so the painful way is to start with the Biot-Savart law and then to just basically integrate. Okay, and so let me just draw another thing on here. So like let's say that I have this like little tiny infinitesimally small segment of wire, which I'm gonna call DL. Okay. So that's I'm gonna mark that on there. So I know that the Biot-Savart law is basically you've got this constant. Um and then I integrate I DL cross R hat, okay, over R squared. Now this DL cross R is basically just like um the cross product between this DL and the direction that connects the point that I'm interested in to that DL. So like R hat is just like this vector here, right? That's R hat. So the cross product between DL and R hat is just going to be one, right? Like this um is just basically DL times sine theta. Or let me call it something different. Let me call it phi. Okay, so it's if this angle here was phi, so that's the angle between R hat and DL. And I know that that's 90 degrees because they're perpendicular. So sine of 90 is equal to 1. So this simplifies down to just like this I DL over R squared. Okay, and I can make another simplification. R in this context, like the distance between the point that I'm interested in and the wire, which is defined as R, it's always going to be the radius of the circle, right? Like the R, as I integrate around like this circle, like as I integrate around this semicircle, the R doesn't change, right? The distance between the point and the arc doesn't change. So I can substitute R here, okay, which is kind of nice. Okay, so this is because every length DL is R away from like this the point that I want to calculate from the point of interest, which is the center of the circle. Okay. All right. So so now what I can do is I can say that the circle arc is going to like the circle arc DL is just going to equal R d theta, where theta is like the angle that I'm integrating around, right? So like if I start here and then I integrate, like I basically do like all of these segments. That's going to be as I go around, that theta is going to change. And so I can substitute DL with R d theta. Okay, so this is just going to simplify down to mu naught over 4 pi. And then it's going to be the integral of I R d theta over R squared. Okay, so now I can cancel this R with one of these R's. Okay, and I can integrate from 0 to theta, right? Over the like angle that I'm interested in, which if I want to know the half of a circular loop, then that's just going to be pi, right? Because all the way around the circle is 2 pi. So like half of a circle loop is equal to pi. Okay, so I'll get the general form from this integral, and then I'll basically substitute in theta equals pi to get the answer for the half circle. Okay, so now so now I just integrate, right? If I integrate, I just get, it's a pretty easy integral. So this is just going to be I theta over R, right? And theta is always measured in radians. Okay. So so this is kind of like the general form. Okay, and if I'm interested in the half circle, which I am, that's what I've been asked for, then theta equals pi, as I just said. So this is just going to be mu naught over 4 pi times I pi over R. So that pi cancels with that pi, and I'm left with mu naught I over 4R. So this would be the B field specifically at the center of a half, at center of half circle. Okay, so this is like this is starting with like the raw like Biot-Savart and basically deriving the B field for a half circle. Okay, let me now do the less painful way. So the less painful way is basically using this result from the Biot, like for a full loop. So this formula here is for a full loop. So it's kind of starting at this point. And then it's using the symmetry of the situation to find it for half of a loop. Okay, and so this, I think you're gonna like this. This is like a lot easier. So you can say that the B field for the full loop is just equal to mu naught times the current divided by 2 times R. Okay, where R is the radius of the loop. Okay, and then you can say to yourself that the arc of a circle of some angle theta is just equal to theta over 2 pi, right? This is sort of like a ratio. Like if, let's say I just want to rotate around like some angle theta, and I want to compare that to like all the way around, the ratio would be just theta over 2 pi. Okay, so if I want to find like the B field of some non-specific arc, I would just multiply that ratio, theta over 2 pi, by the B field of the full thing, which is this. Okay, so that just gives you theta over 2 pi mu naught I divided by 2R. Okay. So let's see. Okay, so and I know, like I did before, I know that the half circle theta is just pi. So I substitute that in for this, right? So that's pi over 2 pi times mu naught I over 2r, right? The pi's cancel, and then 2 times 2 is 4. So I get mu naught times I over 4 times r. Okay. And that's the B field for half of a circle. And it's the same as what I got up here. So like it's just a different technique for finding the B field of some like arc, some fraction of a full circle. You're basically you're taking the ratio and you're multiplying it from, you're starting from a different position. You're saying this, I know from like what I wrote up here. Like you can kind of just remember these 4 things or look them up, and then you never really have to do the Biot survey law. But I did it for you here just so you could see it once. Okay. So the last thing I wanted to talk about in this video is what happens if you have 2 parallel wires, some distance, like let's say r apart from each other, and you have current running through them. And you want to know like what is the force between the 2 wires? Okay, and you know from last week that when you have a current carrying wire, it creates its own magnetic field. And then the magnetic field is going to exert a force on anything that carries a current. Okay, so you have this like kind of double effect. And it's like a very interesting, I think it's like a very, very interesting result. So let's just go through it. Okay. So let's just say I have 2 straight current carrying parallel wires a distance r apart. So let's draw that. So I've got wire, let's call this wire 1. And there's like some current. They both have current of I traveling in the same direction. Okay. So this is my second. Maybe I'll draw that a different color just so it's like really obvious. Okay. So this is the second wire, and it's also got a current I. Okay. And I want to know like what is the force? What is the force? Well, the question is, oh yeah, what magnetic force do the wires exert on each other? Okay, so what's the force between them? Okay. So I'm going to start off by saying, by using the right-hand rule. Okay, and I'm gonna look at it from the perspective of wire number 1. Okay, so I'm gonna put my thumb in the direction of the current, and I'm going to curl my fingers in the direction of the B field. Okay, so the B field is gonna go, and let me draw it in blue. It's basically gonna, there's gonna be a B field that goes kind of like around like this, right? Like lots of, okay. And it's gonna go into the page on this side and out of the page on this side. Okay. So, so that's kind of the first step, is figuring out what the B field from wire 1 is doing. Okay. And then the second step is to say, okay, I want to know what is the force, the magnetic force of wire 1 on wire 2, right? Like wire 2 is feeling the magnetic force from the magnetic field generated by wire 1. Okay. So I know from like the last module that that's just QV cross B, which in the context of current, remember if I integrate, I can just say that the Q, if I add up all the Q's in the wire, it's just equal to the current going through that wire, so current 2, times the length of the wire. right? And it's going to be B sine theta is the cross product. Okay, sine theta is 1 because they're orthogonal, so that just goes to 1, right? So this is going to be the current going through wire 2 times the length of the wire times the magnetic field. And the magnetic field is from 1. Okay, it's from wire 1. Now, I just showed you how to calculate the magnetic field from wire 1, right? It's just mu naught times the current going through wire 1 divided by 2 pi r, where r is like the distance between the two wires, right? It's like I want to calculate the B field. I want to calculate the B field here at that wire, the B field from 1 at that wire. Okay, so here I can just say I2 times L, and then I can substitute this in. This is mu naught times I1 divided by 2 pi r. Okay, and this is the force, the magnetic force of wire 1 acting on wire 2. Okay, so it's important to note that the force that one wire imposes on the other wire is equal and opposite to the force that the other wire imposes on. Like the force of 1 on 2 is equal and opposite to the force of 2 on 1. Okay, so let me just write that. That's important to know. That's basically Newton's third law. Like the force of 1 on 2 is equal to the negative of the force of 2 on 1. Okay, so any force that like wire 1 imposes on wire 2 is going to be paid back by wire 2 on wire 1. Okay, so what I want to do is I want to find the direction of this force. So like this is the magnitude of the force, but what is the direction? So to find the direction, I'm going to use the right hand rule, the second right hand rule, right? So I'm going to put my fingers in the direction of the current. I'm going to fold them into the page, and then my thumb is going to point in the direction of the force. So this is the direction of the force. Okay, this is the force of wire 1 on wire 2. Okay, because they're equal and opposite, I can say that this wire is going to have an equal but opposite force here. So this is going to be the magnetic force of 2 on 1. 2 on 1, sorry. 2 on 1. Okay. So when the current is going in the same direction, the force between the two wires is attractive. So this is an attractive, they're pointing towards each other. It's an attractive force. Oops, force. Okay, I hope you can see that. What if the two wires have current going in the opposite direction? Well, in that case, the magnitude of the force will still be the same. So let's draw that situation. So I've got wire 1. Sorry, wire 1. Let's say the current's going up. This is wire 1. This is wire 2. Current's going down. Okay, let me start kind of in the same way. So I'm going to draw like the magnetic field from wire 1. So my thumb is pointing up. The magnetic field from wire 1 is going into the page on this side of the wire and out of the page on this side of the wire. So this wire 2, is going to feel is going to feel this part of the magnetic force. So like the part that's going into the page. So if I point my fingers down, I use I use the second right hand rule. I point my fingers down, I curl my fingers out of the page. The magnetic force is pointing in this direction. Sorry. Sorry. It's going into the page. I was doing out of the page. It's going into the page. So my fingers are pointing down. They're curling into the page, right? According to this is into the page. Okay, so the force is in this direction. This is the magnetic force of wire 1 acting on wire 2, right? So the current is going down. I fold it, I curl my fingers into the page. See, I can't twist my arm that way, but my thumb points to the right. Okay. I could do the same, like I don't have to rely on this to know that the force, the magnetic force of wire 2 on wire 1 is going to be pointing equal and opposite. I could also just look at wire 1 from the perspective of the magnetic field from wire 2. I could basically do like the reverse of what I just did, right? So I could say like, what is the magnetic field from wire 2? Well, the current is going down, right? So the magnetic field is coming out of the page on this side, right? I'm drawing it in red so that it'll match up with this wire, right? So if I point my thumb down in the direction of the current, my fingers are coming out of the page on the right-hand side of the wire, but they're going into the page on the left-hand side of the wire. Okay, so if I point my fingers up, like here, for this wire, right? My fingers in the direction of V, right? Because that's the direction of the current. So my fingers up, I curl them into the page. My thumb is the direction of the force. Okay, and that's in this direction here. Okay. So when the current is in the opposite direction, it's a repulsive force. When it's in the same direction, it's an attractive force. And this explanation is just sort of like explaining why that is. Okay, so I'm gonna leave it at that, and then in the next video I'll go over Ampere's law, and I'll derive like all of the symmetries that you'll ever run across using Ampere's law. And then that's it. That's it for this week.